Level modeling contest called the Mathematical Contest in Modeling a few years back. So we're going to walk through like how we'll address the problem, and then in the last like 20 or so minutes, we'll talk about the solution that the winning team came up with and compare ours against theirs. So basically the problem runs as follows. So you're given like a distribution of like time and location for serial crimes, and you know that like, in general they come from one killer, right? So this could be the form of like a map where if this is the world, and you know that one occurs here at time 0, and then one occurs here at time 1, and so on and so forth, until you have like a distribution. And the question is, given this data, how can we predict like where the killer lives, maybe, so we can catch him, or like where the next one will be, the next crime, right? So the way that any modeling question works is first you start off by like writing your assumptions about the problem. So can we identify like a few assumptions like as we go forward into the problem? Like, does everyone understand the problem, like how it works and everything? Yeah, what's up?
You said it was a modeling problem.
Yeah.
So you're trying to predict something based on data.
Yeah, exactly. Yeah, so maybe like this serial killer has like a really distinctive like way of executing crimes, right? So we know that like T0, T1, and T2 have the same pattern, and so on. So we can like have like a distribution that's just for one killer. In a more complex case, you'll have multiple, and you have to extract the features of one. But we're not going to worry about that. So if you want to start off with a few assumptions about the world, like what would those assumptions be like? Yeah, what's up?
This was actually like the premise of the first episode of Numbers.
Of what?
Yeah, this is exactly what they did. They had a
Wait, of what show? Like?
Numbers.
Oh, I haven't heard of the show, but okay, yeah. Yeah.
And they had a mathematician, and he figured out where the serial killer worked.
That's awesome, yeah. So, like, do you remember how they started off the analysis, or like?
Yeah, like I know he did this. The mathematician did this one thing where serial killers they try to choose their locations randomly.
Yeah.
But
They want to maximize noise, right? Yeah.
Actually, what ends up happening is that true randomness will not just be evenly, will not be places evenly spaced apart. They'll be clustered.
Right, exactly.
Stuff. But
Yeah.
like humans, when they choose things randomly, it does tend to be evenly spaced out. So that's like one thing.
Yeah, so so you want to make some assumptions about the killer themselves, right? And like that's like the psychological attack you can use to figure out like how this guy operates, right? Okay, so the first one is that I would make is that killers want to kill like as efficiently as possible, right? So what this means is that like just for our assumption, like there's no like privileged target, right? So like there are certain situations where like people will want to kill like one particular person or one particular town or whatever, but like you said, that's not like a random outcome, and it doesn't really help us as we do analysis. So if you say that there's no privileged target, then all the targets are equally likely, and then we can start to narrow in where this guy lives and how he operates, right? The second one, like I said before, is efficiency. So this basically says that serial killers are like human beings, except for the fact that they, go around and kill people, right? So basically, serial killers like don't like waiting in traffic. They're not gonna like go out at unseasonable times of the day or ungodly times of the day, like in the night, unless they actually have to. There's a benefit. They don't like wasting gas and money and fuel, things like that, right? And that's like a pretty important thing for modeling in general, because modeling problems are like oftentimes about like special kinds of things. Yeah, what's up? Yeah, so that's an interesting question, right? So, yeah, procedurally, that probably is the case with people. Like, they'll stake out an area or victims or whatever, right? But this is more for the selection of locations, right? It's like, how do you pick the town to strike it, not so much the person? You could do that kind of analysis for, for person, but that would be, like, a more involved thing, right? So like the heart of this kind of analysis problem or modeling problem is that problems are pretty similar to other problems, right? So like I was doing this thing in high school called like the Moody's Mega Math Challenge, and it asked us to analyze like school lunches, right? And like the insight there is that school lunches like aren't that different from regular lunches. Like they serve the same function and do the same thing. So like the more commonalities you can identify between like people and things that you know about, the better. or things and things that you know about. So in this case, we're saying that our person of interest is similar to people that we know about, like normal, rational human beings, in everything except the goal. And then we can talk about the goal some more. So we also know, like someone mentioned before, that they want to minimize predictability. So basically, serial killers will know that there's someone like us out there trying to look at the data and infer answers, right? So the objective is to try to make the pattern as random as possible. The problem, of course, is that there's kind of an effect there, where if you're trying to consciously make something random, you can't really do that. Whereas if you select things at random, it might not be convenient and so on. So there is a trade-off. So does anyone have any other assumptions about the kind of guy we're dealing with, or as we go forward, or is this good for now? All right, good for now. Cool. So the heart of this modeling problem. Oh damn, it doesn't go down. Okay, or doesn't go up either. Oh wait, I'm just not strong. Okay. Yeah. Okay. Screw it. Yeah. Sure. Do you want to come up and help me with the? Yeah. Awesome. Thanks. And if anyone else. That's how it is usually.
Alright, so what are we supposed to do?
Just help me lift the whiteboard if that's cool.
But how are you gonna attach it to the top?
So, ideally, if you lift it, maybe it sticks or something. I don't really know how this works. Wait, let go and see if it is about to fall down. All right, are we good?
I have absolutely no idea.
Here, let go and see what happens. Okay, yeah, don't worry about it. Wait, cool. Okay. Okay, yeah. Shit. Oh well. Anyways, so you also have to make some assumptions about space, right? Because it only doesn't do so. The heart of a modeling problem is you have to simplify the world in some degree, right? So we've simplified the world as this blank planar space, right? But that's not always the case. And actually, there is the heart of this problem as it was solved is on a more complex version of space. So the way that it's generally done with this is that you look at networks connecting places to other places, right? So if this is Manhattan, for example, you would have a grid, right? So the only way you can get from point A to point B efficiently, if this was a large space, would be to actually somehow use the grid, right? And that leads to what's called the Manhattan metric, which is a better way of finding distance between points. Because if you're looking at this problem naively, and you're oh, so maybe the killer wants to minimize the distance from his hometown to the place so that he can get there quickly, get back quickly, run away, all those things. You might just look at oh, so the Euclidean metric from A to B, or the average distance is if you've seen this formula in algebra, xa minus xb, squared plus ya minus yb squared, and that's your distance. But that doesn't take into account the fact that you have to get there using a predetermined path, right? The path of roads. So if you look at the formula for the Manhattan metric, it's this complicated kind of thing. Something let me take a look. Yeah, so it's the minimum of ways to get from basically, if you sum up over the grid, we can call it over the grid, all the ways to get from A to B, and you take the minimum distance, that's how you can compute the applicable Manhattan metric, right? And this is a better way of computing distance, obviously, and it changes the formula in these instances. So now we can talk about the act of inference. So when you talk about minimizing predictability, what you really want to do is to make what's called Bayesian inference impossible. Bayesian inference is the idea where if you have where you have a likely, okay, so basically Bayesian inference is a way of updating what you believe about the world, right? So Bayesian statistics basically says that we have certain beliefs about the way things are with certain probabilities. We've used this year to find planes. And based on the data you observe, you can update your probability estimation for how things are. So you have this term, P of x, And that's what's called a prior distribution. So like before you know anything at all, like what do you believe about, like let's say where the killer lives, or how he operates, something like that. And then you take some observations. Like maybe you find he struck here and struck there and struck there. And then the question is, all right, so given that information, how do we update what we knew before to get a better guess? So what you do is you compute what's called the likelihood function. The likelihood function basically says that given what we knew about the world before, how probable was it that we actually saw what we saw? So a really simple example would be if you think that a coin is fair, right? So 50% heads, 50% tails, and then you flip it 100 times in a row and you get 100 heads. So the likelihood of having 100 heads, given that the coin is fair, is really, really small, right? It's almost practically zero. So you would multiply that probability times this, and you would get an updated probability, which would basically tell you that the probability that the coin is fair is is in the same way really, really small. This idea is the underpinning of what's called Bayesian statistics, like I said before, and it's really valuable if you go forward into statistics and things like that. So what we did in solving this problem, let me just pull up the thoughts about it real quick, hold on, thoughts on serial killers. Felix, serial. Oh, well. We had a radial approach. So basically we said that if you go back to the plane and you have T0 and T1 and T2, the assumption we made was that the killer would get progressively bolder as the time goes on and he's not caught, right? So let's say he lives here, and first he goes here. It's a pretty small distance, and then he's I'm pretty good at this. Maybe I can, kill someone else. And then he goes here, and it's a farther distance, and then he's no, I'm really good at this. I can, kill someone all the way across the plane, right? So the radius of probabilities expands. So you could use this to kind of triangulate where the guy's house is, right? Because you look at all the points that are let's say some determined radius away from T0 and T1 and T2, and you have rings of probability. Yeah, what's up?
How do you know how he thinks?
Yeah, so that's an assumption that we make, right? Serial killers have a certain psychological makeup. Justifying these kinds of assumptions isn't always rigorously possible, right? Because you don't know actually how the guy thinks. So what we did is you look back into the profiles of serial killers in the past, and they tend to have this kind of idea, where they get bolder and they have this profile, whatever. So you assume that your killer is like that. If it's not, then you're kind of out of luck. But then you have to basically you hopefully early on detect the discrepancy and then say, okay, so let's investigate this some more. So yeah, using this, we kind of said, okay, so here's a formula for figuring out where the guy lives, and then that's the perfect place. Let me look up the formula. But the thing is, that doesn't help you with the charge of the problem, right? Which is predicting actually where the guy's going to strike next. And in modeling problems, it's pretty easy to get sidetracked and forget where the guy actually lives. So we wanted to make sure we were really true to that. So let me erase this. Okay. So let's say going back to the original, you have T0, T1, T2, and a predicted house of here. So the question is, what would maximize the perceived randomness coming out of this distribution, right? So what site location would make it the hardest for police to predict where things are? What would kind of throw us off the scent the most? So what we did was we said, okay, there's a certain distance that these points have together from all the other points, right? So if you look at a given point, P, you can take the distance of all the killing points that we know and add them up, over all the points. And you want to look for points that are, that maximize that distance while at the same time satisfying the other constraints, which is, they're easy to access, but they're not too easy to access. They're close to major population centers, but they're not too close to major population centers. And eventually you'll get like some point over here that's still convenient to get to. It's not like all the way out. And that's like the predicted site for the next killing. This actually leads to like another point in modeling, which is that you don't want to ever have like unconstrained optimization, right? So you don't want to say like just blithely like, oh, we want to maximize the distance from all the other points, because that'll take you to like some point on the other side of the globe that like is perfectly far away from all the other points. And then if you forget to say like on Earth, it takes you like somewhere just like out in space. So you always like sometimes it's really easy to just have like internal assumptions like, oh yeah, of course it'll be like nearby enough that he doesn't have to go like really far. But once you start formalizing like those assumptions, then you get to like the heart of the problem. What I wanted to do now was to like present a formula for finding serial killers that some guy came up with, and maybe see if we can critique it or improve it and things like that. So I'm just going to pull it up. Kim Rossi. Yeah. Sorry?
I thought you said that you entered this contest.
Yeah, so we entered this contest on a different problem, right? So when I say like we did this, I'm talking about like a practice problem that my team did, like based off of like the problem and the winning papers. The problem this year was about finding planes, and we can talk about it like at the end. So I wish I had a projector, but it's okay. Okay, so okay. Equals k. Okay. So this is a formula for based on a distribution of crimes predicting like where a serial killer lives. So basically, what you have is the idea that you have some place that he lives, right? And then you have like a buffer zone of points around where he lives where we assume that the killer isn't going to strike, right? Because it's too close to home, he could be seen, he could be caught, it's like a really bad outcome, right? And then you have the Manhattan distance, which is this, like I said before, the grid distance. So you assume that the world is on a grid like that, between points of the crimes and like the predicted house raised to some power, and plus like a similar term. This is the characteristic function saying like is the point in the buffer zone or not? If it's in the buffer zone, it goes to 0. Otherwise it doesn't. And so like basically what this does is it expresses two ideas. So the first term is you have decreasing probability with increasing distance. Basically like the farther you get away from the house, like the more of a hassle it is to go and kill someone. Like it's just like not worth the trouble. Like just don't worry about it. The second one, however, is first you increase as you move away from the buffer zone towards what's called the hot zone, which is like maybe this. And then it decreases after that point. And the sum of those two effects gives you the probability of living in a certain place. So this formula is notable for a couple of reasons, right? So it's kind of predictive, but like indirectly. Because the way it predicts like where the guy's going to strike next is first by saying, all right, where do we think he lives? Just based upon like the most likely places for him to live. And then based on where he lives, where can we infer that he'll strike next? And the second one is that it has like the reconciliation of two competing terms. One of them being, the increasing distance with decreasing probability. The other one being the hot zone idea. And literally the way it does them is you have one term expressing one of the forces, the other term expressing the other force, and then the sum of those two terms is like the probability and like the thing we know about the world. So that's a generally good way to do things in modeling. Like it works. You can just express things the way that like if I had a particle and I had force F and force G, the force on the particle is like F plus G. Just like from a logical standpoint that works. So I wanted to spend some time like critiquing some of the assumptions in the formula. Like, do you think it's a reasonable way to like describe the world? Like, what situations might this fail in, for example? like what kind of places or what kind of people, like can you make a case that this formula isn't the right way to figure out where like a serial killer lives? What's up?
Well, okay, so,
Is this from numbers again?
yeah.
All right.
Okay, so they actually, so it didn't work out
Hmm.
because they found out that the serial killer didn't actually live in the hot zone, he worked there.
Okay.
It did make the case that not everyone spends all their time at home, like sometimes like
True,
work
true, true.
place is kind of like
So I'm just gonna make a note of like all the criticisms, and then maybe we can like revise them later on, right? And like improve the formula. So. Okay. So the first one is that you have like no, like the wrong home base, right? Or like he's transient. Okay, so that's one objection. Are there any other objections as to like this working or not working? Oh, I thought you were raising your hand. Okay, so like another one might be like this only works for like relatively developed places, right? If you have like a really rural environment where like maybe it's not that hard to get from A, or not that easy to get from A to B on like a defined grid system, then that's a problem, right? So it's dependent upon like environmental context. And the third thing, and like, you should always be really critical when you're approaching a model, is like why would the hot zone thing even work? Like what's the actual like underlying justification for a killer not wanting to kill like in his hometown or home state or whatever, or like home county? Does anyone have plausible reasons as like why you might or might not want to? Like, yeah, what's up?
Patriotism.
Sorry?
Patriotism.
Oh, like towards your town, like. You're like, oh, so I'm only gonna kill like outside the downtown area, so I can, yeah, like that's a plausible thing. So this is actually like a good example of the kind of thing I was talking about before. So if you have to start like imposing restrictions upon like the object of study that makes it like really hard to imagine, maybe they're not like the best restrictions. So like I can imagine someone who's like a patriotic person who's like fiercely loyal to like his neighborhood or whatever, and he wants to kill all the other neighborhoods or something. But like in actuality, like most people don't operate that way, right? So that's why you would kind of shy. Like, I see what you're saying. You have to give a defense, right? But that's why you would shy away from making that kind of justification, just because it is a little bit like unrealistic. Quantifying realism isn't like that easy of a thing to do. But like the best way to imagine it is like the principle of like minimal change. So like if you have like an average human being, like how many things you have to change to make them into your object of study, right? So like you'd have to add the fact that like they kill people. That's like an assumption, but like you would add it in the way that like they want to kill people, in the way that it makes them happy, right? So it makes them happy just like buying cake makes people happy, or doing things that makes people happy. It's not like some kind of overriding addiction or imperative necessarily, right? And if you add it in that way, it's like a really like less invasive kind of thing. You can work with people in the context of theories that you know, and econ and psychology and all of that kind of thing. So like then you can say, okay, so if people are like that, if killers are like us, except the fact that they kill, then we can use basic econ facts, right? So like you have the idea. Have you guys heard of like the rational human being in econ? Basically, it's the idea that human beings are like rational and self-interested people. It's called like Homo economicus, and it's like kind of defining like a certain set of parameters. So basically, it says that human beings have a utility function, U of a certain set of inputs that they want to maximize, right? The inputs might be things like money and free time and all these different things, and they want to maximize that by increasing profits and minimizing cost, right? So costs are things like time spent going from A to B, money spent going from A to B, like the psychological damage of things going from A to B, and obviously profits are money and happiness and goods and things like that. So you can then just literally inherit the theories from econ, and that's the way to go. You can also derive the boldness thing about going further, because you have like psychological studies done on people, which says that like the better they get at doing things, like the more risks they'll take, right? So like the better they get at doing math, maybe they'll take harder math classes, and eventually they'll crash and burn or something. But like for now, they'll be okay. Or like in athletes, for example, I think you can do these studies where like the better you get at like playing soccer, like the more risky passes you'll take, the more things you'll do that are colorful and flamboyant, as opposed to just like playing the game, right? So any questions on anything we've covered so far, or should I move on? Yeah, what's up? Copycats? Yeah, so that's an interesting conundrum. Was that like in the show, or is that like? No, that's. Oh, an original insight. Awesome. Yeah. So this is a good objection, because when it sees to the heart of the problem, right? Which is that like you're not dealing with like inanimate objects, you're dealing with like human beings, right? So the way you would justify the copycat assumption is saying, okay, so being a serial killer makes some people really happy, and this guy is providing like an easy way to do it, so other people would want to be really happy and do it also. Yeah. And the really good thing about that objection is then like that lets you like process the data better. Because let's say like instead of this nice and easy like system, we had like a bunch of points that had the same pattern of killing, right? Like a bunch of people trying to be equally notorious and equally like vindictive as this guy. So the way you would maybe correct for copycats, and we can work on this later, is to look at the time evolution and to like subcluster the data. So what you would do is you would look at all the data, and you would find some technique for clustering it, or you would just heuristically cluster it, which basically means you would just like eyeball it, and then you would see if that checks out. If they evolve and define patterns that all follow the formula, then you can identify 2 or 3, maybe 4 killers of that kind. Yeah. So can we maybe like start to revise the formula, like, or maybe write one for like a different case? Like, let's say, goddamn, yeah. I don't know how math professors do this because they're not really strong people, right? Like, okay, so. Yeah, so let's say you wanted to write a formula to predict where a serial killer lived in like a rural region. So maybe there's like maybe it's this kind of region where you have A, B, C, D, E, and F are your towns. And the towns are connected like that or something. So have you guys, by the way, ever heard of graph theory? Yeah. So yeah, what's up?
I thought you were like.
Oh, like raise your hand if you heard of. Yeah. So if you've ever seen the movie Good Will Hunting, there's a guy who like draws like these kind of things like on the board at MIT. Those are graphs, right? And graphs are ways of connecting like sets of points and like visualizing like sets of points with connections. And this is actually like an example of a graph in graph theory. So what we can learn, like just like from that observation, is that you can oftentimes pull in like abstract and different kinds of mathematical analysis when you're solving like a practical problem. So like for an example, when we were studying like the problem in the MCM this year was how do you predict, like given that how do you better find planes that go down, like Malaysian Airlines 270 or whatever, like is there any way you can improve the searching process? So what we did was we divided the ocean up into a grid, just like that. And we said that every time you do a search, you're collecting information about the way the world is at time 0, right? So even if you search here and the plane isn't there, like that's something valuable. Because if the plane isn't there, let's see at time t equals 1, and you know that like ocean currents flow in a certain way, like let's say the ocean currents flow like towards that point, right? Then you know the plane wasn't here at time, let's say t equals 0. Like, we assume that time was discrete, so it moved in steps. But like it's the same kind of idea for continuous. Like if you know where something is, that means or something isn't, then you know where it wasn't one instant before if you know the laws of motion, right? And then we kept on going, and the idea was to use this formula, Bayes' rule, to help us like optimize the search. So like pure math like can really inform math modeling. So anyways, like back to this, right? So what kind of assumptions can we make about like rural serial killers that are different or revised from those about urban and suburban serial killers? Like just like spitball. Like, there's no like really right or wrong answers. Just want to get like something to work with. Or it's like 4:30 and like you don't want to think on Saturday, which is also really okay. So we can just start saying things like, you know, so the one thing is like daylight is pretty critical, right? Because in rural areas, you don't have like, you know, oftentimes like, you know, well-lit streets or, you know, like well-paved roads. So having daylight to get back home is a really critical thing because oftentimes it doesn't work out that way. I mean, yeah, you have like headlights on your car, but the roads aren't perfect and you oftentimes have animals walking around. Like, it's not a safe situation, right? So that kind of gives you like an imperative. So maybe there's one imperative to, you know, kill in daylight or something. And then there's another imperative to get back home quickly, because obviously there's a downside to killing in daylight, which is, you know, you can be seen easily by like a neighbor or something like that. So then there's an imperative not to kill in daylight. And literally, like if you did the math and you added them together, then I expect you'd have someone like, oh, so like the optimal time to do these killings is somewhere like twilight, right? Where it's, you know, dark enough to be, you know, secret and shrouded, but not so dark that you can't get home, right? But then you have another imperative, which is you don't want to kill at a regular time, because then the sheriff's going to be like, all right, so we're just going to keep an eye out on all the people in twilight, and then we're going to, you know, like find you eventually, because we're going to be really vigilant during this time. So then you have like a, you know, not to be regular. And you know, if you were doing like a really simplistic model, you could add up like all of these different effects, and you could get like the, you know, like a decent model of how these things worked. So the interesting thing about this is that we just like started with like, you know, one principle, right? Oh, so there's not that much light, you know, in rural areas, and then we derived this imperative and that imperative and this one derived on top of that, and you just keep on adding like more and more detail and complexity to these models, right? Which is the way that, you know, these things tend to work. One of the mistakes that people make when they're doing like math modeling is they start off with like a bunch of crazily complex, you know, assumptions about the way the world works, and then they realize that we just don't have the time or the data to actually like, you know, work these through. Moody's and the MCM, they're like 4-day or like, you know, 1-day competitions, and it's really on you to like find all the data yourself. So you don't have time to like, you know, just make a really crazy, like if we wanted to be complex, we could talk about like, you know, like the fact that most people who live in, you know, rural areas do a certain kind of work, they farm, and farming gives you a certain kind of mindset, like you're more capable with your hands, and, you know, maybe you'll like strangle people as opposed to like, you know, kind of doing it like the cowardly way or like shooting them or something. But like we don't have the time or the support to make all these kinds of assumptions. So we focus on like what's really essential, which is that farmers are people that are trying to kill people, and here's, you know, like how it happens. Any questions so far or anything like that? Cool. So going back to the plane question, just wanted to talk more about like modeling theory. So you had the company that produces these. One good thing that you have to be able to do in modeling is actually find the relevant facts about the world. So if I asked you guys to like, you know, find where planes go down, like how they go down, what are some questions that you might want to get answered before you start doing the work? What's up? Yeah, like what actually causes a plane to go down, right? Anything else? Just like random questions or like things that you would look up before you started doing the, yeah.
What kinds of planes go down?
Yeah, what kinds of planes? Yeah, keep them coming. We'll do like 3 or 4 kinds of questions, and we'll talk about like how we solved them through. Or is this like, okay, yeah. So the first question was a really interesting one, because we assumed that, so one of the things you can do when you're solving modeling is you don't have to account for like every situation that's different as its own class of thing. Things fall into groups, right? So let's say this is like the map of like a piece of Earth, like airspace or ocean space. So we identified 2 main categories for planes going down, right? Or like causes. We identified weather-related events and 3 actually, sorry, human-related events and mechanical events, right? Like 3 different independent things. So we said, okay, so let's assume that like weather events are randomly distributed amongst the place, and, you know, mechanical events randomly happen, and, you know, people-related events randomly happen. And that's like a fine way to do it. But then we thought, okay, but we have to investigate the correlation between these different things, right? Have you guys read a book called Outliers by Malcolm Gladwell by any chance? Yeah, so I think he studies the plane problem in that book. And what he says is that people, like, communications errors tend to be like a big thing when, planes go down. And people oftentimes might communicate less effectively when they're in like a panic situation, like a storm or something like that. So you can draw a correlation between like weather having an effect on people and weather having an effect on machines, which also have an effect on people. So the important thing with these factors is to identify like the chain of causality, right? Like people can't change the weather, the plane doesn't change the weather, but the weather is like the source of data from which we can work backwards and update, what we believe about the probabilities of these things. The second one is like what kinds of planes, and that's like a really good question too. So we looked up like passenger airlines and commercial airlines. And like, yeah, so military airlines are more robust and they don't go down like as often, whereas passenger airlines they split up and cause debris and that kind of thing. So it's really important not to assume that your problem is homogeneous, right? So like if I gave you like the general serial killer problem, which is like if the police commissioner just gave you a chart of all the serial killings, or of all the killings in a certain town or a certain like city or something, and said I want you to find the people responsible, you're not going to assume that they're all the same kind of thing, right? You're going to try to isolate out, like, okay, these ones seem random, these ones are motivated by this person, these ones seem to have this distinctive style. And then you'd start to isolate different groupings of data points. And that's something that's really valuable also. We also wanted to look up facts like about the world at large, right? So when it turns out that planes have this like really sophisticated handshake system when they talk with satellites, right? It's called like, I think it's just called like a satellite handshake. And it gives you like the location of the plane at every point in time for 15 minutes, at t equals 0 and 15 and 30 and so on over the course of the flight. And finding existing data sets really makes your life a lot easier. So one of the things with serial killers is that they don't like to drive through toll booths, because toll booths, take your picture and they use, Easy Pass, and that's like a really, risky outcome for a serial killer. So if you have data about, like, for example, how the toll booths are distributed in like this place, like maybe if you're going back to our like rural example, there's like a toll booth, here and here, and all the killings occur over here, then we can kind of cut this town out as a probable location because it involves going through a lot of toll booths, for example. So learning facts like about the world is a really valuable thing when you're doing a modeling problem. It says here that the formula was used in the pilot episode of Numbers. So one last thing I wanted to talk about is the idea that these characteristic functions, like these Booleans, are really very valuable because not like all the conditions are triggered like all the time. So in the Rossmo formula, you had this function. You had ij, where it's 0 in the buffer zone and 1 outside it. Have you guys covered like piecewise defined functions in math class or anything like that? Yeah, right. So these functions like in math class are really like kind of stupid and contrived, but like in the actual world they actually do a lot of good work because it touches on the difference between a discrete and a continuous problem. Continuous problems are those that where every value like matters, if that makes sense. Or like where things change constantly as you move along a place, right? So a continuous problem would be like, all right, so how far are you from the buffer zone? And you can compute that value for like each point, in a given space, and that's valuable. But what Rossmo is saying is that, that information really isn't valuable. What's valuable is, are you inside the buffer zone or are you outside it? Like the rest doesn't matter, which is why you use like a discrete function like this. So just remember that like the choice of your function always like matches like the information that's important. So if you want to look at distance, that's really important to the problem, then you'll use a continuous function. If only being inside or outside matters, then you'll use this. And that's like a really solid thing. The last thing I wanted to talk about, we have some time, is using computers to solve these, like AI to solve these kinds of problems. So there's something called, so most people who do modeling today will use computers a little bit. And there's something called like an artificial neural network, which is like a really nice way to solve like statistical problems. And the way that neural networks work is they try to simulate like what happens in the human brain with the assumption that humans are good at solving problems. It's like sometimes not a well-founded assumption, but sometimes it is. So you have like a couple of input neurons that take like data, and the data is like passed off to like neurons inside a hidden layer of neurons that like no one sees, but they do computation, and then those are all passed off to the outside, right? And that gives you your output. And the way that you use a neural network is you train it on like a bunch of data, right? So you give it like a matrix of like past serial crimes, and you say, all right, I want you to extract like the what do you call it? Like the essential features of this data set and use it to work on other data sets. Do you guys see any potential pitfalls with that idea? Okay, well, the two common pitfalls are that training is really hard, and novelty is really hard. So like I was watching this TV show called Psych a while ago, and like on Psych, what you have is this like really like notorious professor like serial killer who like kills everyone in this really like idiosyncratic way. And if you just trained like a neural network on like normal psychological properties, it would absolutely fail on, I think they were called like Dr. Yin and Yang or something, because these people were so crazy that it was beyond what was imaginable before. So that's a kind of example where statistics doesn't work, because like the assumption here is that things that happened in the past are like the things that happen in the future, and that's not always the case. The second example is training. The second problem is training, because the way you have to do training is you have to pick just enough data points that you get like the common features about what's important, but not too many that it only focuses on those data points, and not too less that it doesn't recognize anything. So the good example is like if you train a network to identify a face, because if you give it like too many faces, then it focuses on identifying those properties of faces that are common to like all the different faces in the data set. And as you keep on adding faces to the data set, like the number decreases, right? Like the number of common structural elements between faces just will like statistically decrease as you add more disparate elements to the set. But if you give it too few, like if you just give it one face, it'll be like, oh, this thing is kind of elliptical. So watermelons are also like faces, and other things are like faces. So it'll just give you like everything that's like that, even though it's not the case. So when you use computational techniques like this, you want to restrict, and appropriately size the training matrix. And the really cool thing about these problems is they work in like a lot of dimensions, right? So you have like other ways. So there's something called a support vector machine, which is basically, it sounds like a lot cooler than it is, like most things in math. But like you basically have like a bunch of points, and it attempts to draw like lines or planes or hyperplanes, which is like 4 or 5 n-dimensional planes that separate the points. So you then have a classification. Like, oh, so if the points are close together, then they're together in the same class, and otherwise they're not. And these problems oftentimes take on like hundreds and thousands of dimensions, because like the number of different parameters by which you measure people and things get really, really larger, right? Like if you're measuring a face, you have like the angulation of the face, the general complexion, the shape, like the eye inset, the nose offset, all of these different things, and that's like a really high dimensional vector set, which is why like still machine learning is like a really challenging endeavor. And why like simple mathematical heuristics like this, or like what used to be over there, are oftentimes like more successful. I think we pretty much covered what we had to cover. But if you guys have any questions about like anything I said, or math in general, or current Splash, I'd be happy to answer them. If that's, yeah, what's up?